Hi, I'm John Paulraj, and this is part 11 of the Complete Solution series for May 2025 IB Math AI HL Paper 1 Time Zone 1. Let's roll the intro. So here we are on 11, question number 11, and this is a question on geometric sequences. Predominantly, I think it's a question on geometric sequences. What makes this question interesting and probably, might throw some people off is the inclusion of a complex number. All right. Now, I did hear at the end of the May 2025 exam, some of my students came up to me and said that, it was more algebraic. And I see that. I'm not saying it's completely untrue, okay? I think there was some signature campaign and all that kind of stuff, that happened right after paper 1, that is, okay? And this is just the time zone 1. We haven't even seen, as of now, time zone 2 or time zone 3 for that matter. But it does seem true, okay, that it does have a lot more algebraic flavor to it. And in the earlier parts, if you've missed out, you might see that I've made references that, maybe the IB is now expecting HL students, whether you are AA or AI, to have at least a fair bit of command over your algebraic skills, all right? And so that's not to say that this question is solely on complex numbers. This particular question, I think, what I got to know was there was so much more of complex numbers. Inverses or something like that. I'm not really sure, okay? I can't remember what this was, sometime in May, of course. So now, at the time of the recording of this video, this is already November 14th, Children's Day, all right? Although the video might go up on the 15th, all right? So happy Children's Day, all across India, it's celebrated. Forgot to mention in that earlier video, but since, I'm just talking rambling rather than talking. 14th of November is when we're recording this, and I mentioned that is because May 2025 is when this paper just happened, and I think students came up to me and said something about inverses or something like that, and I wasn't really sure. But I'll show you how you can do this thing, even if you're an AI HL student, with the use of your graphing calculator. And at the same time, as I said, that I think it's becoming more and more clear that there is an expectation that AI students also should have a fair bit of command over their algebra. Having said that, as I said, this is predominantly a question on geometric sequences, but with a nice complex tone. Let's check it out, okay? Nanthana, I don't know how you pronounce her name. I'm sorry if there's someone called Nanthana here who's listening to this video, but that's the best I can do. Nanthana is completing an exploration on multiplication using complex numbers. Okay, so her exploration is on complex numbers and on multiplication using complex numbers, and it's nothing on multiplication later on, okay? So it's nothing about her exploration, so much about the geometric sequence, okay? She considers a geometric sequence where U1, the first term, is 9, and the common ratio is 203 plus 203i. That's the complex number. You have to write down the value, write down. Sometimes when we see the word write down in the IB, you just have to write down. And as you can see, it's just 2 points. That means it's possibly 1 and 1 point, okay? So not much of working required, because it's just write down, simply write down, not as opposed to show that or bring it in a certain form. But you all know that for a geometric sequence, if U1 is the first term and R is a common ratio, then you know that U2, the second term, is given by U1 times R. There's a multiplication involved, and with the value of U1 given to you 9, that's 9, and the value of R given to you as, what was that, 2/3? Okay, 2/3 plus 2/3 I, all right? There will be some kind of multiplication. Now you can do that, but it is just to write down. So what we're going to do is that we're just going to say using GDC, using the graphing display calculator, and we will write down, as I've said, we will write down exactly what we enter. Now, when we do that, I just need to make something clear. As I always said that, we insert a new problem for every question. And the last problem, meaning question number 10, was something unique, okay? If you notice that every question we have a page, a unique problem defined on our graphing calculator, but there's nothing for 10. You see that? 8, 9, and the current problem for the current question number is 11. So, which meant that was a first question where a graphing calculator was not required, and that kind of makes me wonder whether that question was so purely algebraic. Okay, typical paper 1 AA kind of paper. But anyway, let me know in the comments what did you think of the last video. All right, if you have any feedback about that. But anyway, here we are. So what I'll do is, so that it's not confusing, if you run into this issue, here's another tip. Okay, insert a new problem and call it problem number 10. Okay, leave it blank, because this is problem number 11. Why am I saying this? Nobody's going to ask for your calculator, right? Nobody's going to ask for your calculator. But the tip I'm offering is basically because when you're checking your work at the end of the exam, when you're checking your work on the paper, you'll know that 11 corresponds to 11. Even that confusion should not be there. So get into the discipline that, the question number that you have on your paper should coincide with the problem number on the calculator, so that that's easy to verify. Okay, this question, what are the calculations involved? You can straight go up there. And we saw that there wasn't any calculation or calculator involved in question number 2. I left that blank, but still created a problem. So that, at the time of checking your work, it's there, and there's less confusion involved. Let's put it that way. All right, having said that, let's get on to this question. What I'm going to do is that I'm just going to go ahead and define U1. I'm going to define, so control and the key to the right hand side of 9, U1 as 9, and it'll just say done. And then I'm going to define R as the term as they've given, okay, the complex number as it's given, control, and that's 2/3. And then there's a plus, and another 2/3, I believe, 2/3. And remember, there's an I. The I is found here along with the pi, this key. All right, so here we go. That's my I. So I have defined the symbol colon and equal to. That's for define. It's gone into the memory. Told the calculator that this one is U and this one is R. What do we need to calculate? We need to calculate U2, and we will just compute. Okay, so I'll just say U1. It'll come as bold times R. We can just say that. Don't need to show the algebra. 6 plus 6i, just like that. So how do you represent this in your on your answer? Okay, so we come back and we just say that using GDC, and here you can spell it out. You can say U1, and you can put the same syntax. Okay, U1 you defined as 9, and R you've defined as, what was that, 2/3 plus 2/3i, and therefore U2 is U1 times an R. That is equal to, you can just write down 6 plus 6i. This is perfectly all right. And that is because the question was write down. It was not so much about show that. Okay, remember the keywords. Okay, and you've already told the examiner that you're using the GDC. This is how you've entered. All right, you've also demonstrated that you know how to find, okay, what is the formula to use to find the second term. So in the same way, you can do the part 2 also. It says write U3. Okay, so if U2 is that, this is A part 1, if I'm not mistaken, this is A part 1, okay, and the part 2 for U3 is just U1 times R square. U1 times R square. Okay, so we'll do the same thing. We'll go back to our calculator again, and you can just say that again. You can say using GDC, and simply you've already shown that was what you defined, right? You can write down using GDC, and let me just go back to my calculator, and we'll do the same thing. We'll say U1 times R square. So R and the square of R, and you hit enter, and it's 8i, just like that, 8i. All right, so we just have to copy. The question says just write down. So this is basically U3 equals, if you want, you can show the substitution. I would say go ahead and show the substitution. Okay, that's 9 times, you can write down 2/3 plus 2/3i, show the square. You don't have to actually write down what the square was, but you can then write down this is equal to 8i. Clear? There you go. That is meaning of write down. Okay, now next part of the question involves Nanthana claims that the sequence of the absolute values, okay, of each of those terms, U1, U2, U3, also forms a geometric sequence. So the original sequence was U1, U2, U3 with those conditions given to you, but the sequence of absolute values, that is the modulus, okay, some people like to use the word modulus, also forms a geometric sequence. And this is where that one little thing about the complex number is involved. And for those of you who are not aware, let me just quickly say that for you. This is from the earlier question. So if you have a complex number, typically represented as Z or Z, depending upon which part of the world you come from, then the absolute value or the modulus of Z is given by under root of A square plus B square. Okay, That's the idea, all right? That's the idea of the absolute value of z. So I think what they are saying is that, you know, the sequence of absolute values, if u1 is the first term, then, you know, it's just purely real number, then the absolute value of u1 is just 9 as it is. But u2 we can just see u2 is a complex number, right? u2 is a complex number. There we'll need to find the absolute value, okay? That will be a different term. And then u3 also is a complex number, purely imaginary in this case. Can you see what I'm showing? Okay, you know, that's my u2 and that's my u3. There we'll have to find, you know, what the absolute value is, you know, using that formula that we have. But actually the calculator will do it for us, okay? So what Nantana is claiming is that the sequence of the absolute values also forms a geometric sequence. Show that Nantana's claim is correct, stating the exact value of the common ratio for the sequence. Let me just take a minute and explain what the IB means by exact value. Oftentimes, when I'm talking to students about this, you know, they all ask, why are you going into so many details of explaining every term? So you should know what they're expecting now. Tomorrow, you know, after you write, and teachers, if you're watching this video, you know, just make sure you do the same thing so that children are not caught up. Exact value means no decimals. Simple, no decimals. So leaving your answer as a multiple of root 2 or a multiple of pi, or as a fraction. But simple terms, exact value means no decimals. Is that clear? All right, so coming back to our question, you want to write down the value of the common ratio for this new geometric sequence as an exact value without a decimal. All right, so let's just do that, and I'm going to continue it here since there's no space here. So this is 11, I think, part B, and we have, you know, you can write down u1, comma u2, comma u3, and u1 was 9, and this is what was that, 6 plus 6i, 6 plus 6i, and what's that, u3, 8i, and you can put a dot, you can see what I've written, okay, is where the sequence of absolute values u1 equals u2 equals u3 equals, and you let the space because now you're going to jump into the calculator and use the calculator to find out the absolute values or the modulus of each of those terms. Okay, so let's just do that. Come back to our calculator screen. Okay, and now the absolute value is here. Here, okay, so if I just go ahead and do that, let me just see if I just use the absolute value, whether it'll give me, or whether I have to do that formula under root of. Okay, maybe on the safe side, I think let's just do that. Okay, so let's just go ahead and insert the square root symbol here, and u1 is 9, so the square root of 9 square, remember the real part is all that is there, so square root of 9 square, the answer should just be 9 in this case, right? That's just 9. And this is the next term. That's the real part is 6, and the imaginary part is also 6. Okay, so what we're going to get is, we're going to get, I'm just going to up arrow, oopsie, what did I just do? I did something wrong. Okay, let's do it again. Arrow up again, and then bring it down. Then we'll just edit that term. Remember, real part, this is my u2, u1 plus u1 times r. This is my u2. So the absolute value is basically the square of the real part, add the square of the imaginary part, and then take the square root, which is what we have. Both the real part and the imaginary part are 6 in this case, so it's 6 square plus a 6 square. So it should be 2 root 6, I believe, if you write it with, 2 root 6, or did I say 2 root 6? 6 root 2, sorry. 6 root 2. Okay, this is the second term, the absolute value of the second term. Then the third term is this one, u1 times r squared. So that's 8i. Real part is 0, imaginary part is 8. So that again, will be just 8, I believe. Okay, so that's 0, and that is 8. Okay, oopsie, 9. What did I say? When I'm writing 9, I'm saying 8, and when I'm writing 8, I'm saying 9. Okay, there you go. So this is the absolute value of the first term, this is the absolute of the second term, this is the absolute value of the third term. All right, I'm just going to write down, this is 9, and this is 6 root 2, and this is 8. Okay, okay, and so I'll just share my screen back here. And then we can say this, and we can say using GDC. Make sure you mention that, okay? Make sure you mention that. U1, U2, U3 is this thing using GDC. This is what it is, okay? Now you'll find the common ratio because that's what you're looking for, showing that it's a geometric sequence. So you can just say that the difference between U2 minus U1. Okay, take the difference. Okay, this is going to be equal to, not difference, sorry, ratio. Okay, ratio of consecutive terms. Difference would be for arithmetic sequence. Okay, so this is 6 root 2 divided by 9. Okay, 6 root 2 divided by 9 is simply 6 root 2 divided by 9. And if you're comfortable doing that, or I can show it on the calculator also, this is just going to be 3, 2, 3, 3. This is just 2 root 2 over 3. This is the ratio of the second term to the first term. How about the ratio of the third term to the second term? You can write that thing down also as the ratio of U3 divided by U2. Can you guys see this? I hope you can. All right, so here you go. This is nothing but 8 divided by 6 root 2, and so that is nothing but 8 over 6 root 2, which is 2, 3, 2, 4. Okay, but because there is a square root in the denominator, you can simplify that, which sometimes we refer to as rationalizing the denominator. Basically, it's multiplying the numerator and denominator by that root 2. So when you do that, you have 4 root 2 over 3 times root 2 times the root 2. Okay, so that's root 2 times the root 2. There you go. So this just simply becomes 4 root 2, and 3 times 2 is 6. Now this simplifies to 2, 2, 2, 3, and you're getting 2 root 2 over 3 again. See that? This is the ratio of the third to the second, and this is the ratio of the second to the third. Both the times the ratio is the same, and then we can say that therefore U1, U2, U3, blah blah blah, dot dot dot. What's the language of the question? I always try to keep the language of the question. Also forms claims that stating the exact value of the common ratio. Exact value, like as I said, is without decimals. Also forms geometric sequence and we have all the words here. Yes, with the common ratio. You could have written R, but I don't know whether I wrote R earlier on, so I don't want that confusion. The common ratio is 2 root 2 over a 3. Clear? Right? 2 root 2 over 3. Make sure you copy that correctly. Okay. So you've shown, how did he show? You've just taken the ratio of consecutive terms and take both. Okay. Don't just take one, because that's how we show that it's common. Otherwise, it's just a ratio between U2 and U1. You'll get 2 root 2 over 3. Make sure you show that the ratio of U3 and U2 is also 2 root 2 over 3. That justifies indeed the ratio is common, all right, between any two successive terms. All right, I think then we had the last part, which is part C, which says that hence, and I think I have also discussed this word earlier, and hence, that key term, the command term, hence, it means use the result from above. Use any of the results from the above in the early parts. Hence, find the sum of the infinite sequence. Apparently, the sequence of those modulus terms, those absolute value terms, is an infinite sequence. You've got to find the sum to infinity, okay? And we know the formula. That's a straightforward use. And this is just extending. I'm not sure whether I'll be able to solve the next question on this. Hopefully, I will be, but we'll see, okay? When we come to that, we'll solve that. So what am I going to do? I'm going to just make some space here. Okay. I'm just going to make some space here. This is 11C, all right? And sum to infinity, infinity, okay, I hope I got the spelling right. Okay, of that geometric sequence, S infinity is basically the first term divided by 1 minus R. The first term is 9, and the R we just found out to be 2 root 2 over 3. 2 root 2 over 3. Let's just simplify that. We got 9 over 3 minus 2 root 2. The whole thing divided by 3. And I think we can just use our graphing calculator now, because, you know, that's all that we're looking for The IB will check whether you know how to substitute, and then it's just about using the GDC. So here I can just say using GDC. Okay, the final value. Okay, just let me just jump over, and I'm just going to enter the expression as we want. So we have a ratio, and that's 9/1 minus. I put another ratio there as it is. Okay, 2√2. So it's 2 square root of 2. There you go. Square root sign over 3. Okay. So the expression just as it is, you don't have to evaluate. I hope this is the exact value. Okay, that is the exact value. If you want the approximate value also, we can get that. So we can bring that thing down and hit Control Enter, and at 157. 157, really? Is that the exact value? Is it? Yeah, it's like 3SF 157. So let's do that. Both of them, we can write both of them together. Okay, the exact value and the approximate value. So I can just come to my calculator screen and say this is 27 2√2 plus a 3, which is approximately 157. Okay, so I think that's all the time that we have for this particular video. If you found something useful, please make sure that you like, share this video with somebody, and make sure you subscribe to my channel. If you do visit my channel, there are several other videos. Do check them out, and leave a comment if you want some question, if you have a topic or some concept that you'd like explained. Do leave that in the comment and I'll make a video for you.